Hello, and welcome to the video lecture for topic 12, or I should say part 1 of the video lecture for topic 12, acid-base reactions. Now, there's two sides to acid-base chemistry that I'd like to cover in these video lectures. The first being acid-base reactions and what you're going to be expected to demonstrate in problem sets and in exams. And then the second half, or the part 2 of the video lecture for topic 12, is going to cover factors that influence the strength of an acid or the strength of a base. So the first half, what we're going to get into right now, is just talking about acid-base reactions in organic chemistry. And in organic chemistry, we have two theories that we like to use for acid-base chemistry: the Lewis theory of acid-base and the Bronsted-Lowry acid-base theory. And so we're not going to do a whole lot with Lewis acids this semester. They are going to appear in later topics, specifically topics 19 through 21, when we do electrophilic addition reactions. But they are going to play a very heavy role in the chemistry that you see in 202. And so I'd like to give a brief introduction to Lewis acid-base theory at the beginning of this video lecture. So Lewis acid-base theory is all about electrons. And so for our Lewis theory, any Lewis acid is any species that can accept a pair of electrons. So Lewis acids are all electron acceptors. The opposite of that is what we would consider a Lewis base. So a Lewis base is anything that can act as an electron donor. So let's take a look at a few examples of Lewis acids and Lewis bases. So our common Lewis acids, and I'm going to begin to abbreviate these as La for Lewis acid and Lb for Lewis base. So in organic chemistry, some of our more common Lewis acids are elements such as boron, aluminum, iron. We also frequently see sodium, lithium, and potassium serving as Lewis acids, right? In Chem 201, boron is going to be the most common Lewis acid we interact with. Again, that's going to be in topics 19 through 21 this semester. But next semester, you're going to make frequent use of iron and aluminum, and occasional use of sodium, lithium, and potassium, all as Lewis acids for some of the reactions that you're going to be learning about. Now, the common feature between all of these elements is that when they serve as a Lewis acid, they have an open orbital that can accept electrons into them. And we've seen this before with boron, in that boron is neutral when it has 3 bonds and an empty p orbital, and that p orbital can then accept electrons from another species to create what we're going to find out is called a Lewis acid-base adduct. And we're going to see an example of that here in just a moment. And so these are all electron acceptors. Now I'm going to throw one more Lewis acid in here that we're going to see when we come into Bronsted-Lowry acid-base theory. And that other electron acceptor is a positively charged hydrogen atom, right? The proton. So the proton is a electron acceptor. It can receive an electron pair and form a bond to another atom. And so it fits our classical definition of a Lewis acid. It is able to accept an electron pair. Now Lewis bases, which I'm going to abbreviate Lb, right? So for our Lewis bases, the most common Lewis bases that we're going to interact with this semester and also next semester are nitrogen Lewis bases, which have a lone pair of electrons that they are able to donate to a species. We're also going to see oxygen appear as a Lewis base. And again, oxygen has 2 lone pairs, right? And so it can use those as, it can serve as an electron donor. One that we're going to see more frequently in Chem 202, but I'd like to make you aware of now, is phosphorus. So when phosphorus has 3 bonds to it, it behaves similar to nitrogen and it has a lone pair. And so once again, it has a pair of electrons that it can use to donate into a Lewis acid. So it can donate electrons into a Lewis acid. And so all of these Lewis base species will notice that they always have some sort of lone pair that they can donate to another atom or to another group. And so all of our Lewis bases are electron donors. Now, when a Lewis acid and a Lewis base react, they form what's called a Lewis adduct. And so we've actually seen this before in Chem 201. So if you recall, we have seen boron trifluoride react with diethyl ether. And so if we draw this out, here's our boron atom. We're going to have 3 fluorines on this boron atom. And it also has an open p orbital, right? That's unfilled, and it's neutral in this state. If we take a look at diethyl ether, we have an oxygen that has 2 lone pairs, and so it can serve as a Lewis base, right? Boron here is our Lewis acid, and the oxygen of diethyl ether is our Lewis base. And what we can have happen is one of these lone pairs donate into the empty p orbital of boron, and what we generate is a compound known as boron trifluoride etherate. And I'm just going to go ahead and abbreviate that BF3, right? And now we've formed a new bond to this oxygen atom. Okay? And so we've made this adduct, and what we find now is that if we use the mathematical equation to determine our formal charge for boron, we'll find that it has a minus charge, and we'll find that the oxygen atom, if we repeat the process, now has a positive charge. And so when a Lewis acid reacts with a Lewis base, we form what's known as a Lewis adduct. So this is now a Lewis adduct. Now, the example I've given has, right, charges on both our Lewis acid and our Lewis base. That's not always going to be the case, but this process of some sort of a Lewis base, an electron donator, using one of its lone pairs to form a new bond with a Lewis acid, an electron acceptor, will always generate a Lewis adduct for us. That's really all I'm going to get into in terms of Lewis acid base theory. And now I'd like to move on to the Bronsted-Lowry acid-base theory, which is what's our primary concern here in 201. While Lewis acid-base theory is all about the ability to donate or accept a pair of electrons, Bronsted-Lowry theory, which I'm just going to abbreviate BL, Bronsted-Lowry acid-base theory is all about the ability to donate or accept a proton, a positively charged hydrogen atom. And so Bronsted-Lowry acids are proton donors. And Bronsted-Lowry bases are proton acceptors. Right? And so, because here now, in our Bronsted-Lowry acid-base theory, our primary concern is the ability to donate or accept a proton, the way we're going to think about this, or the way that we're going to qualify the strength or weakness of our acids and bases, is based off of this ability to either lose a proton for an acid or the ability to gain a proton for a base. Right? And so this process of losing a proton is known as acid dissociation, right? And so we can write a generic reaction for acid dissociation where we have some fictional acid, which is going to be a hydrogen atom attached to something else, which we're just going to call A, right? And it is we're interested in how easily it is able to separate to break that chemical bond, right? Or to have this proton dissociate from the rest of the acid to form these two species, H plus and A minus. Right? Your acid may not always end up with a negative charge, but it will always gain a new electron pair, right? A new lone pair of electrons when this dissociation occurs. And so this is an equilibrium process, and so we can write a equilibrium constant. I'm not going to get into the math of that equilibrium constant and how it's determined. That I think is covered very nicely both in your POGIL worksheet and in the Sorrel textbook. But I'm just going to refresh that we call this equilibrium, we have a specific term for this equilibrium constant, right? This is the Ka, and Ka is a measure of how much HA wants to turn into H plus and A minus, right? And so Kas typically are written as 10 to the power something, right? 10 to the power x of some sort, some number x. Now, now this exponent on our power of 10 here, this power of 10 exponent, right, tells us a lot about where this equilibrium is going to lie. Now, for a strong acid, which really favors dissociation, right, x, our exponent here, is going to be a positive number, right? And for acids that don't like to dissociate, they prefer to stay hydrogen, proton bonded to the rest of the acid, right? So that where the equilibrium lies on the HA side, right, x is negative. And so we can say that if x is a positive number here for our equilibrium constant, this is going to indicate that we have a strong acid. And if x is a negative number, that's going to indicate that we have a weak acid. Now, organic chemists are incredibly efficient. As you've seen before, we don't like drawing out full structural formulas, so we find a much faster way to write it if we're going to draw out a structural formula, and that gives us our line structures. And similarly, we'd like to be a little bit more efficient with our time, and as opposed to writing 10 to the x to describe this equilibrium, we use instead what is called the pKa. And so the pKa, right, of an acid is equal to negative log in base 10 of Ka. So we can rewrite this now, knowing that Ka is going to be some number that's 10 to the power x, right? So we can rewrite this as negative log in base 10 of 10 to the x, which is just going to equal negative x, right? And so now we can begin to use this to quantify the strength or weakness of an acid. And just for a simple example, right, if our Ka, let's say, is 10 to the negative 7th, right, our pKa is going to be negative log in base 10 of 10 to the negative 7. Right? Solving that gives us negative times negative 7, which just equals 7. And so we have to do this switch in our minds when moving from Ka to pKa, in that a large pKa means that we have a weak acid, and a small pKa means that we have a strong acid. Right? So we can say that if x is positive, we have a strong acid, right? And we have a low pKa. And that if x here is negative, we have a weak acid, and that's going to give us a high pKa. So, right now, what we need to do is start looking at acid-base reactions and how we can use, right, this knowledge of pKa's for our acids and bases to be able to determine, right, favorable equilibria in acid-base reactions. So I'd like to start off with a relatively simple example of acid-base reactions, the dissociation of HCl, hydrochloric acid, in water. And so we're going to write out our species that are involved in this reaction. So we have water. And whenever we're looking at a reaction, we want to make sure that we have all lone pairs showing, right? So we have water, and we have our hydrochloric acid. Right? And the first thing we need to do is determine which is going to be our proton donor and proton acceptor. Now, I've already told you that this is hydrochloric acid, so we know that that's going to be our proton donor. And that means that by definition, water here has to serve as our base, and it's going to be our proton acceptor, right? The oxygen of water has 2 lone pairs on it. One of those lone pairs can be used to form a new bond to hydrogen, which will break the hydrogen-chlorine bond. We remember that all acid-base reactions are equilibrium reactions, so we'll use an equilibrium arrow. And then from there, we'll draw the products of our reaction, right? And so now we've generated a new species. Excuse me. Where we've created a new oxygen-hydrogen bond, and now that oxygen atom takes a formal positive charge, and we've made a chlorine anion. Here now our chlorine has gained a lone pair when the hydrogen-chlorine bond broke, and so it takes now a -1 formal charge. And so now, if this is our acid, this is our base, right? We can give names to the new species that we created, right? Once our acid gives up its proton, it is now able, this chlorine ion, it is now able to accept a proton. And so it is a base. And in our reaction, we would classify this chlorine anion as a conjugate base. And I'm going to abbreviate conjugate because it is the base that was created from our original acid dissociating. Similarly, water began as our base, but now here, H3O+, it now has a proton that is able to donate. It is now an acid, and so we would call this the conjugate acid of our H2O, which was our base. Right? To determine which side of this equilibrium is favored, we need to compare the pKa's of our 2 different acid species. So we have HCl as one acid, which has a very, very low pKa, right? So this has low pKa, and it's approximately -6. H3O+, our conjugate acid, also has a low pKa. Its pKa is approximately -2. Acid-base equilibria always favor the weaker acid. The weaker acid in the equilibrium will be the acid that has the larger pKa value. Since -2 is larger than -6, H3O+ is our weaker acid. HCl is our stronger acid. And we can say that this side of the equilibrium is favored. Now you'll notice here that I don't assign any numerical values to the strength of our bases. That is because in organic chemistry, we live in a strictly pKa world. Now, In other classes and in other fields of chemistry, you will hear chemists talk about a pKb as the measure of a strength of a base. That's fine. They're welcome to do that. But in organic chemistry, we don't use pKbs, ever. We live in a strictly pKa world, and so even though we've heard of this thing called a pKb, and we know that other people like to use it, and we're fine if they choose to, we don't get into that whole mess of pKbs. All we ever think about is pKa's. And so in order now, right, for us to be able to qualify how strong or weak a base is, we do that from knowing the pKa of the base's conjugate acid. So here now, I have my conjugate acid of H3O+, which was generated from my base, H2O. A weak acid generates a strong base. And so because my H3O+ is the weaker acid, by definition, my H2O is my stronger base. And because HCl is my stronger acid, by definition, my conjugate base, Cl-, becomes my weaker base. Another way for us to say this is that strong acids form weak conjugate bases and weak acids form strong conjugate bases. Now, this is a fundamental rule that we are going to find to be true for all of our acids and bases that we deal, or at least our Bronsted Lowry acids and bases that we're going to deal with in Chem 201 and 202. And so this is something that we really need to commit to our memory. Whenever we see a strong acid, HCl, low pKa, we know it forms a weak conjugate base. Whenever we see a weak acid, we know it forms a strong conjugate base. Now, these are comparisons just for these equilibria that we do, right? We can't just fundamentally say that an acid is strong or weak without having something else that we compare it to, right? So these are all used to make qualitative comparisons between different acid and base species. So let's take a look at another example where we talk about the strength or weakness of a base. So for this example, I'm going to use a nitrogen base, and I'm going to use one of the more common nitrogen bases that we see in organic chemistry, known as triethylamine. So I have a nitrogen with 3 ethyl groups off of it, and a lone pair so that it is able to accept electrons. And I'm going to use an alcohol oxygen-based acid. Here specifically I'm going to use methanol. And I know that triethylamine is my acid because it doesn't have a proton to donate. And I know that my methanol is going to be my base because it does have a proton to donate. And so this is going to also be an equilibrium process, right? All acid-base reactions are in equilibrium. My arrow pushing for this reaction goes like this. Lone pair on the nitrogen forms a new bond to our hydrogen atom, and that hydrogen-oxygen bond breaks to create a new lone pair on oxygen. And so my 2 new species are protonated triethylamine. Nitrogen now has 4 bonds, no lone pair, it takes a positive charge, and deprotonated methanol. Oxygen has 1 bond and 3 lone pairs, and a formal negative charge. So now I can do the same comparison I did before. I have my proton acceptor, my base. I have my proton donor, which is going to be my acid. My base, after it receives a proton, forms the conjugate acid. And my acid, after it loses a proton, forms a conjugate base. Now, again, I can only compare pKa's, right? I can't compare pKb's. And so, if we refer back to the table of pKa's that was handed out for topic 12, we'll know that we estimate our acids of having our OH acids, similar to methanol or ethanol, we estimate those to have roughly a pKa of approximately 18. We know that if we refer to that same chart, right, we'll see that protonated amines, these ammonium species, right, have a pKa of roughly 10. Again, we make no comparison between our base and conjugate base because we don't use pKb's in organic chemistry. And so here now, comparing between our starting acid and our produced conjugate acid, we see that the higher pKa is for our starting acid, which tells us overall that the reaction favors this side of the equilibrium. So this is our favored side of the equilibrium. Right? We can then further go and compare the strengths of the two acids and two bases that we have. Right? So if we look at our conjugate acid, it has the pKa of 10 relative to our starting acid, which has a pKa of 18. We would say that this is the stronger acid, and that methanol was our weaker acid. And if we use our rules that we have up here, we'll see that means, by definition, that the conjugate base of my strong acid is going to be the weaker base, and my conjugate base from my weaker acid is going to be my strong base. And so this is how we evaluate acid-base equilibria to determine what is likely to occur. Now, just because the free triethylamine and the protonated methanol, right, just because this side of the equilibrium is favored, doesn't mean that we don't have a little bit of these species existing in solution as well, right? It just means that the dominant form of our nitrogen species, right, of our initial base, is going to be in its basic form, in its deprotonated form. And that the dominant form for our methanol, our acid species, is going to be in its protonated form. We're still going to, if we were to take some super powerful microscope, or if we use some spectroscopic technique that could tell us about that could detect the presence of either our conjugate acid or conjugate base, we would find that there is some of our conjugate acid present, there is some of our conjugate base present, but in very small amounts. If we want to know exactly how much of those are present, we have to do a lot of math. That is a valuable skill that you should be able to do, right, for other chemistry courses. But for our purposes, it's going to be enough to know which side of the reaction is favored and which form is going to be dominant, right? And so one last rule that we're going to put that's a corollary to strong acids form weak conjugate bases, weak acids form strong conjugate bases, is that we're going to add on to there that acid-base equilibria always favor the weaker acid. Or the side that has the highest pKa. So now we can take this one step further, and if we look at a couple of acid-base equilibria, we can actually make determinations on which bases are stronger than others, and which acids are stronger than others as well. Now, I'm just going to do this. I'm going to leave this for you to do as part of your POGIL worksheets and as part of your textbook reading. And from here, I'm going to move on to the last skill that you're going to need, right, for acid-base, or one of the last skills that you're going to need for part one of our discussion of acid-base chemistry, and that's being able to determine ionization states of acids and bases at a given pH in solution. So, oftentimes we're interested in knowing, right, what the ionization or protonation state of a chemical species is at a given pH. Now, this becomes particularly important for biochemistry considerations when we take a look at amino acids. So I'm going to draw up an amino acid and walk you through how we can determine its protonation state at various pHs. So one of the nice features of amino acids for this type of an exercise is that there are multiple sites in that molecule that are going to either be acids or bases. And so I believe that this is serine that I'm drawing, but don't quote me on it. I don't have my amino acids memorized, or at least not anymore. So if we just draw a overall neutral form of our amino acid, and now here we want to draw full Lewis structures so that we can really be able to see which sites are potentially Bronsted-Lowry acids and which sites are Bronsted-Lowry bases. We'll see that we have three functional groups here that can serve as acids or bases. And so we have our carboxylic acid functional group, we have an alcohol functional group, and we have an amine functional group. Now, I may be putting this into a solution that's pH 1 or pH 7 or pH 14 or any other pH. And I'd like to be able to predict which of these groups are going to be protonated and which of these groups are going to be deprotonated. And so the first step in doing this is to write out the pKa's for each of these functional groups. Or, if it's a basic functional group, the pKa of the conjugate acid. So, just starting with our carboxylic acid, which only serves as a proton source, we know that its pKa, if we reference the chart that was given for topic 12, is approximately 5. For our nitrogen, right, so for our amine group, we know that it's going to serve as a base typically, and that the pKa of the conjugate acid, so now here I'm going to go pKa, but this time it's for the conjugate acid, right, which I'm going to abbreviate Ca, is approximately 10. And then finally, we have our alcohol. Now our alcohol, if we refer to our chart, can either be a proton donor, because it has this hydrogen off the oxygen, or it can serve as a proton acceptor, and because it's got these lone pairs on the oxygen as well. And so we want to list the pKa's for both of those eventualities, right? So its pKa as an acid is approximately 18, and its pKa, the pKa of its conjugate acid, again now we're going to have in the conjugate acid we have two hydrogens off of this oxygen and a positive charge, so the pKa of the conjugate acid is approximately -2, right? So that's our first step. List out the pKa's for the acids and the pKa of the conjugate acid for any base. Sometimes you might have a functional group that can either serve as an acid or it can serve as a base, and so we need to put both of those values down. The next step to determining the protonation state is to draw for ourselves a number line. And so we'll just draw a nice horizontal line. And from there, make that a little bit longer here, give us plenty of room to work. And from there, we're going to list out in order, right, from lowest to highest, the pKa's of the different functional groups that we have. So our lowest pKa is -2. Next, we have a pKa of 5. From there, we have a pKa of 10. And from there, we have a pKa of 18. Now, you don't have to space these out perfectly. You just need to space them out so you've got a little bit of room to work. After we've listed our pKa's, we want to write the form on each side of that pKa that the potential acid or base can take. So what do I mean by that? Well, starting with our -2 pKa, right? If we know that it can exist, this oxygen, when we refer to it as being a base and a conjugate acid with a pKa of -2, it can have two forms, right? Either the first form with one hydrogen as a base, or the second form as an acid with two hydrogens off of that oxygen. And so, to the left of my -2, what I'm going to put, or to this side I should say, still haven't gotten left and right down in these videos, but to this side of my -2, I'm going to list the protonated form of that base. So that would be RO, two hydrogens, a lone pair, and a positive charge. To the other side of that -2, I'm going to write the basic form for that pKa. So this would now just be ROH, and we have our basic form if that functional group is going to serve as a base. For my carboxylic acid, on this side, I write COOH, the protonated form, and on the other side of that pKa, I write the deprotonated form, COO-. Moving forward now, I've come to my amine. To one side of that number 10, to the lower side of the number 10, I'm going to draw the protonated conjugate acid form. So that's going to be RNH3+. And to the higher side of the pKa, I'm going to write the basic form, which would be RNH2 with a lone pair on the nitrogen. And then finally, I come to my alcohol functional group, this time now serving as an acid with a pKa of 18. To the lower side of 18, I'm going to write out my acidic form. That would be ROH. And then on the higher side of that 18, I'm going to write my basic form. That would be RO-. Here now, I'm all set up to determine the protonation state at any pH that I'm given. And so now I'm going to walk through first what happens at pH 1, then at pH 7, and then at pH 14. So if I take my amino acid and I put it into a solution at pH 1, to determine its ionization or protonation state, I'm going to mark that pH of my solution on my number line. So 1 would go here, between -2 and 5. So here we're going to evaluate at a pH of 1. Next, I look at each of these functional group possibilities and find which form is closer to the pH I marked. So for my alcohol, this form is closer. For my carboxylic acid, this form is closer. For my amine, this form is closer. And finally, for my alcohol acting as an acid, that form is closer to my pH. And so now I know what the protonation state of the different functional groups would be at a pH of 1. And I can redraw my molecule at that protonation state. So here now, I would start off with the basic framework. And now I'm not adding in any of my acidic hydrogens just yet. I'm going to leave that 2 off of my hydrogen on my amine as well, just until I'm ready to put what's going on in. And I'm going to leave that bond to that alcohol oxygen open. I'm going to leave the bond to the carboxylic acid oxygen open. So I go through my functional groups one at a time. I see that my alcohol has a hydrogen on it. I can put that in. My carboxylic acid has a hydrogen on it. I can put that in. And my amine has 3 hydrogens and a positive charge. So I would put NH3 and a positive charge on my nitrogen. I can now complete my Lewis structure for this molecule, adding in lone pairs. And I now know that this is the ionization state or protonation state of this amino acid at a pH of 1. So at pH 1. Now what happens if it's at a pH of, let's say, 7? I repeat this same process. I would mark that pH on my number line. So 7 here between 5 and 10. And I would once again evaluate which of my forms for each functional group is closer to that pH. So once again, I see that my alcohol, right, is going to be, if the alcohol is serving as a base, it's going to be in its deprotonated form. The carboxylic acid will also be in its deprotonated form. Now my amine is also in its protonated form. And finally, right, my alcohol serving as an acid is in its OH form. So once again, I can draw my molecule. Here now for my amine, I'm protonated, so I have an NH3+. My carboxylic acid is deprotonated, so I have an O-. And finally, my alcohol is ROH. Right? And so now we can just say that this is the protonation state at a pH of 7. Finally, we're going to repeat this process one more time at a pH of 14, just so that we've gotten a little bit more experience and we've demonstrated this one more time. So here now I'm going to once again mark my pH at 14, right, between 10 and 18, and I'm going to check to see which of my functional group states are closer. So here now, alcohol acting as a base, it's going to be in the ROH form. Carboxylic acid, the deprotonated state, is closer. Now my amine, right, my RNH2 state is closer to that pH. And my alcohol acting as an acid, right, is closer in its ROH state to pH of 14. And so now I can draw the third form that I would potentially see of this molecule, right, at a pH of 14. Here now I've drawn my basic framework, and I go through my functional groups once again. ROH is protonated. That puts a hydrogen onto this oxygen. My carboxylic acid is deprotonated. I have my O- with all of its necessary lone pairs. Here now my amine is in its free base form, so I have a lone pair on my nitrogen, along with 2 hydrogen atoms, and my alcohol doesn't change, it stays consistent based on what we had down here. So here now we can say that this is the protonation state at a pH of 14. And if we look at this, it makes pretty good sense, right? For at a low pH, so under very acidic conditions, we would expect the sites of our basic sites to be protonated. We would expect our acidic sites to also remain protonated. As we move to neutral pH, right, pH 7, so now it's less acidic. We have an equal balance between acid and base. Now it gets a little bit tricky. Based on the specific pH, we're going to need to determine, right, for functional groups like carboxylic acid and amine, right, these very obvious functional groups, we're going to need to determine, is it protonated, deprotonated, and that's going to be based on the pKa of the acid, or in the case of a base, the conjugate acid, right? And so we can make those assessments there. And then finally, at very high pH, so these are under very basic conditions, we would expect our highly acidic groups, like our carboxylic acid, right, to be deprotonated. We would expect our basic groups, because we don't have free protons floating in solution at low pH, or excuse me, at high pH, we would expect that to be unprotonated as well. And then for our functional groups, right, that have unique pKa's that don't really fall in this traditional range of their pKa's, would be somewhere in the range of pHs where we normally go from 0 to 14, right, we would need to do this sort of an evaluation, and we would see that our alcohol is protonated, right? So this is a skill that's going to be expected of you in 201. You're going to be expected to be able to do this kind of analysis in 202, right? Picking what we saw earlier, picking the more favorable side of an equilibrium. That's going to be expected of you in 201 and 202. And then finally, this protonation state determination is going to be a valuable skill for you in courses such as biochemistry, and even potentially in some of your biology courses as well. And so I hope that, part 1 for topic 12 has been informative for you. And as always, if you have any questions, please feel free to bring them into conference, lecture, or office hours. Here's the warning. There's going to be 2 videos for topic 12. We've talked about acid-base equilibria, we've talked about protonation states, we've talked about the fundamental nature of the 2 acid-base theories we have in organic chemistry. And now part 2 of topic 12, or video lecture 2 for topic 12, is going to get into the factors that influence the strength of different acids and the strengths of different bases. So make sure you watch both video lectures for topic 12. Thank you.